Today's rabbit hole, I over-engineered my morning coffee. I've done this for years. Every morning I make coffee. I have a grinder, a scale, a kettle with a temperature display, a pour-over dripper, and what I can only describe as a deeply unearned confidence that I know what I'm doing. Turns out I had no idea what I was doing. Not because my coffee was bad. It was fine, maybe even good. But fine and good, they are completely unmeasured, unverifiable, unreproducible assessments based on nothing but the fact that I was tired and it was hot and it had caffeine in it. I aspire to be an engineer. I build systems. I optimize things. And I was making one of the most chemically complex beverages in the human diet every single morning, using nothing but instinct and old wives' tales. So I went looking for the actual science, and I found it. And it is so much weirder and deeper and more unhinged than I expected to make a YouTube video about it. We're going to talk about extraction yield, total dissolved solids, partial differential equations, a reinforcement learning agent trained to make your pour-over coffee, and the fact that the golden rule of brew temperature that every barista will die defending is, according to peer-reviewed research, probably fine to ignore. And then I'm going to show you the 3 tools I built to solve a problem that didn't need solving. The chart nobody shows you. There is a document that has existed since the 1950s that defines in measurable engineering terms what a good cup of coffee actually is. It's called the Coffee Brewing Control Chart. It was developed by a chemist named E. Lockhart, working with what eventually became the Specialty Coffee Association. And it is essentially a process control diagram, the kind of thing you'd see in a manufacturing plant, except instead of tracking widget tolerances, it's tracking the chemical composition of your morning cup. The chart has 2 axes. The vertical axis is the brew strength, measured as total dissolved solids, or TDS. This is literally the percentage of your coffee that is dissolved coffee compounds rather than water. A typical well-brewed filter coffee lands somewhere between 1.15 and 1.55% TDS, which sounds absurdly low until you realize that the remaining 98+% is water, and that tiny fraction of dissolved material is doing all the flavor work. The horizontal axis is the extraction yield. This is the percentage of the dry coffee grounds that actually ended up dissolved in your cup. You put in, say, 20 grams of coffee. What percentage of the mass of those grounds made it into the liquid? The target range is 18 to 22%. And in the middle of the chart, where those 2 ranges overlap, there's a zone, the ideal zone, the region where, according to the organized taste panels going back decades, coffee is more consistently rated as balanced and enjoyable. Outside that zone, you get failure modes. Under extract, below 18%, and the coffee tastes sour, thin, and grassy. The good stuff never made it out of the grounds. Over extract, above 22%, and it goes harsh, bitter, hollow. You pulled out the good compounds and then kept going until you got the bad ones too. High TDS with correct extraction, strong and intense. Low TDS with correct extraction, weak and watery. The chart accounts for all of this. It is a 2-dimensional map of every possible way your coffee can go wrong. Almost nobody measures either of these numbers at home. Baristas know this chart exists. Coffee professionals use refractometers, little optical instruments that measure TDS, to dial in their brews. But the average home brewer, including me for years, is operating completely in the dark. We adjust the grind size because a YouTube video said to. We use a 1 to 15 coffee to water ratio because that's what we read somewhere. We brew at 93 degrees Celsius because that number has achieved the status of religious doctrine in specialty coffee culture. But none of us actually know where we're landing on the chart. I wanted to know, so I started pulling on the science. And that's where things got strange. Every variable is a lever. Here is the engineering reality of coffee brewing. Your final cup's position on that control chart, the TDS and the extraction yield, is determined by a set of input variables. And every single one of those variables is a lever. Move one and you move the dot. Let's go through them. Grind size is the most powerful lever you have. Finer grind means more surface area in contact with water, which means faster and more complete extraction. Coarser grind means less surface area, slower extraction, lower yield. This one is intuitive. What's less intuitive is that the grind uniformity matters almost as much as the grind size. When you grind coffee, you don't get uniform particles. You get distribution. A bell curve of particle sizes with some big chunky pieces and some very fine dust called fines. Those fines extract almost instantly and can push you into over-extraction territory while the bigger particles are still barely getting started. This is why expensive grinders are expensive. They produce a tighter, more consistent particle distribution. You're paying for uniformity. Brew ratio. The ratio of coffee mass to water volume directly controls TDS. More coffee per unit of water, higher TDS. This one is almost mechanical in its predictability. The Coffee Science Foundation at UC Davis found that the TDS is actually easier to control via brew ratio than any other variable, which makes intuitive sense when you think about it. You're literally controlling the concentration by controlling the inputs. Water temperature. Okay, this is where the received wisdom starts to crack. The 93-degree rule. Everyone knows it. 93 Celsius. Some people say 91 to 94. Some say exactly 92. It is the most confidently stated number in home coffee culture, and I've heard it repeated 1,000 times. UC Davis ran a comprehensive 2-year study co-led by a chemical engineer and a sensory scientist, underwritten by Breville, evaluated by 118 human tasters. And they found that the brew temperature, when TDS and extraction yield are held almost constant, has very little measurable impact on flavor. When you control brew strength and extraction, the actual outputs on the control chart, the temperature you use to get there barely matters to the people drinking it. Now, temperature does affect how fast and efficiently you extract. Hotter water extracts faster. It's not that the temperature is irrelevant. It's that the temperature is an input to the extraction process, not an end-state variable. What matters is where you land on the chart. Temperature is just one path to get there. The 93-degree rule is essentially an operationalized shortcut for a particular style of brewing that got cargo culted into universal law. This will make some people very upset. I don't make the data. Water chemistry. This is the variable that Coffee YouTube almost never talks about, and it might be the most important one nobody measures. Water is 98 to 99% of your cup. The mineral content of that water, specifically the hardness and alkalinity, the concentration of calcium, magnesium, and bicarbonate ions, directly affects which flavored compounds get extracted from the grounds and how completely. Magnesium ions are particularly interesting. Research shows they selectively bind to certain aromatic compounds in coffee, effectively pulling more of the good stuff out. Calcium affects extraction differently. More body, slightly different flavor profile. Bicarbonate acts as a buffer that affects the acidity on the final brew. The Specialty Coffee Association has an entire water quality handbook. There are people who mix their own brewing water from distilled water and mineral salts specifically calibrated for coffee extraction. If you're using straight tap water with no idea of its mineral content, you are introducing a completely uncontrolled variable into your brew every single morning. Your coffee might taste different on different days, and you might blame your grinder when the real answer is that it rained last week and the municipal treatment changed. Extraction time and flow rate. These are interrelated, especially in pour it over. Slower flow means longer contact time, means more extraction. The geometry of how you pour, how you distribute water across the coffee bed, and how evenly the grounds are saturated, all of this affects the uniformity of extraction. Non-uniform extraction is its own problem. If water channels through part of the coffee bed and barely touches another part, you get over-extracted coffee mix with under-extracted coffee, and the result is an unpleasant combination of bitter and sour simultaneously. Now, I told you it gets weirder. In 2015, a group of applied mathematicians at University of Limerick, working with researchers from Philips, published a model of coffee extraction from a drip brewer, a mathematical model. The full version is a system of coupled partial differential equations describing mass transport, dissolution kinetics, and fluid flow through a porous bed of coffee grounds. The paper itself notes that the full equations can only be solved numerically and describes the complete model as something only a computer could love. They then spent the follow-up paper deriving simplified asymptotic solutions because the full model was too computationally expensive for practical use. This is the level of engineering effort that has gone into understanding your drip machine. And then in 2025, last year, a group of researchers published a paper in PeerJ Computer Science in which they trained a reinforcement learning agent to optimize pour-over coffee brewing variables. The RL agent learned to balance grind size, brew ratio, water temperature, and extraction time, as well as TDS by exploring the parameter space and maximizing a reward signal based on whether the resulting brew landed in the ideal extraction zone. It achieved 90% accuracy in predicting optimal parameter sets, outperforming decision trees, k-nearest neighbors, and support vector machines. Somebody trained a machine learning model to make better pour-over coffee. The model won. The escalating absurdity. So I built a spreadsheet. You put in your brew ratio, your grind setting, your estimated extraction yield, and it plots your position on the brewing control chart. It shows you the ideal zone. It shows you where you are relative to it. It tells you whether you're under-extracted, over-extracted, too strong, too weak, or theoretically perfect. It's a reasonable tool, useful even. A normal person might stop there. I did not stop there. I built an interactive HTML version of the brewing control chart because if I'm going to be showing you this on a screen anyway, it should be interactive. You should be able to click your position on the chart. It should highlight the ideal zone. It should be something you can actually use during a brew session on your phone or laptop sitting next to your kettle. A normal person would definitely stop there. The Python TUI, that's where I ended up. You enter your brew parameters, it calculates your estimated extraction yield using the standard formula. Extraction yield equals beverage weight times TDS divided by dry coffee weight. It takes a refractometer reading if you have one. It plots your position on an ASCII representation of the brewing control chart rendered in your terminal, and then it gives you a specific actionable adjustment. Grind finer, adjust your ratio, check your water, try a longer bloom time. It runs in a virtual environment. It has a config file. It has a command line interface with flags. I built a command line coffee advisor. Here's the thing though, after going through all of this, reading the papers, building the tools, measuring my brews with an actual refractometer, I did learn something real. Not that the tools were necessary, they weren't. A skilled barista can taste extraction problems and correct them without any of this. The tools are ridiculous. I know they're ridiculous. But going through the process of building them forced me to actually understand what each variable does and why. I'm not adjusting my grind because a YouTube comment said to. I'm adjusting it because I understand the relationship between particle size distribution, surface area, extraction kinetics, and where I land on a two-dimensional quality map that was developed by a chemist in the 1950s and validated by UC Davis in a 2-year controlled study. Coffee is a system. Every system has inputs, outputs, and transfer functions. The inputs are grind size, ratio, temperature, water chemistry, and time. The outputs are TDS and extraction yield. The transfer functions are the partial differential equations that the University of Limerick mathematicians spent years deriving. You don't need to know the math to make good coffee, but knowing that the math exists, that this is a real studied engineered process with measurable outcomes, changes how you interact with it. You stop tweaking randomly and start developing hypotheses. You stop chasing magic numbers and start understanding why those numbers exist. And occasionally you build a Python TUI that does something a $4 refractometer and 30 seconds of mental math could do faster. But we don't talk about that part. The spreadsheet, the interactive chart, and the Python tool, I could put in the description and put on a GitLab if you're interested. You could use them or don't use them. Judge me for building them. All valid choices. I'll see you in the next one. If you like this, subscribe.